Welcome to a new microeconomics video lesson in this section regarding to game theory. With this video, we begin to look at the last type of games, those with imperfect or incomplete information, also labeled as Bayesian games. In the games studied so far, players know everything they need to know about the game, including the strategy profiles of the other players and even their payoffs in every alternative. However, there are other types of strategic situations in which at least one of the players is unaware of relevant information, which is called private information held by some player. Nevertheless, these players know or can know the probability distribution over those unknown parameters, so they can make inference about the likely effects on their respective utility and make decisions in a rational way. Some real-world examples of these Bayesian games are, for instance, sealed bid auctions, where only the bidder knows the bid they submit and does not know their rivals' bids. Another example is competition between firms in duopolic markets through prices, since, as seen in other subjects, such as industrial organization, firms need to know their rivals' costs, and this information is generally private, although they can form assumptions using probabilities about different likely scenarios for their rivals. In this video, the necessary tools will be studied to analyze Bayesian games in which not all players know everything they need. This adds realism to the game's analysis, but also many mathematical complications. A game is said to have incomplete information when at least one of the players has relevant private information. That is, when at least one of the players is unaware of relevant information. For example, some of their rivals' strategies or some of the payoffs obtained in some outcome combinations. Bayes' rule will be used to make inferences about unknown information. The importance of this rule in this type of games has led them to be known as Bayesian games. One of the first key concepts for analyzing games of incomplete information is the type of a player. By the type of a player, we mean the private information that only that player observes. Therefore, each player knows exactly his or her own type, but doesn't know the types of the rivals. In fact, for a game to be considered one of complete information, at least one player must be unaware of the type of at least one of their rivals. Although players may not know their rivals' types, the probability distribution over these types can be no common knowledge. Moreover, if a player has private information, his or her strategies can change depending on that player's type, and the opponents will have to form expectations about the likely outcomes via expected utilities, based on the probabilities they assign to each type of the rival. For example, consider price competition in a duopoly. A firm may suppose that its rival has either high cost or low cost, with probabilities Q and 1 minus Q respectively. The opponent firm knows exactly what its cost type is, high or low, and its strategy can vary according to this information. The firm with incomplete information must compute its expected payoffs, taking into account both likely rival types, since it is uncertain about which one is the true type. Let us now look at how to represent a game with incomplete information. Consider the following payoffs matrix of a simultaneous game where player 1 has two strategies, U and D, and player 2 has another two strategies, R and R. The difference with the matrices seen in static games with complete information is that in one of the final payoff cells, the strategy pair U and L, there is a parameter X that identifies player 1's type. In this case, player 1 knows exactly what his true type is, so he knows the value of X before the game is played. Player 2, however, doesn't know the true type of his rival. He only knows that X can take the values 20 or 12 with equal probability in this example. Therefore, in this example, player 2 has incomplete information because he does not observe the true value of the parameter X, whereas player 1 has private information because he doesn't know the value of X before playing. In this kind of situation, player 2 knows that he may be facing one of the following two games in the slide with equal probability. As can be seen, the two games are very similar. They differ only in the value of the payoff received by player 1 when the pair U and L is played in each of the two games, depending on the two types that player 1 may have. Of course, probabilities in this example are half and half, but they can differ in other Bayesian games. To conclude with this introduction to Bayesian games, another way to represent the previous incomplete information game is using the following decision tree. We are assuming there is a fictitious player, usually called nature or chance, who determines player 1's type. In this case, X is 20 or 12 before the game begins. In fact, what this representation does is to link the two games from the previous slide through the move of this fictitious player called nature. This representation is due to Albert Harsanyi in 1967.